Hello, my dear students. Welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today I'm going to start with a series of hybridization, and today's topic for the lecture is the sp hybridization. For sp hybridization, let's take a example of beryllium chloride, and it's BeCl2. The beryllium chloride shows sp hybridization, or more accurately we can say the central atom beryllium in this case shows the sp hybridization. Why we have taken the central atom to be beryllium? Because beryllium is forming, in this case beryllium is forming two bonds, whereas one chlorine forms only one bond. So the atom in a molecule forming maximum bonds is taken as the central atom. So beryllium will be the central atom in this case. So we will talk about the beryllium, the hybridization of the beryllium. Now, I have taken beryllium over here. What's the atomic number of beryllium? It's 4. Then what will be the valence shell electron configuration of the beryllium? That will be 2s2 2p0. So now let's make the orbital diagram in the form of boxes. Now the 2s subshell will have one orbital, that's 2s, and 2p subshell will have three degenerate orbitals. What's degenerate orbitals? The orbitals having equal energies. So that's 2px, that's 2py, and that's 2pz. Now let's fill the electron. The 2s is having 2 electrons. So the first electron in 2s with a spin of plus 1 by 2, and second electron in again 2s with a spin of minus 1 by 2. So this is called the ground state of the beryllium. Now, as we know that when the orbital have only one electron, only then it will overlap with the other orbital having one electron to form the covalent bond. But in case of beryllium, we are not having unpaired electrons or a single electron in a single orbital. So here what's gonna happen? In this case, the electron from 2s will jump from 2s into the 2px orbital. Jump, or we can say more accurately excite. The electron will excite from 2s orbital to the 2px orbital. So this thing comes out to be it's like this. One electron is over here, another over here, and this is called now excited state of the beryllium. Now here two orbitals are having two electrons, so now beryllium is eligible to form two covalent bonds with the two atoms of the chlorine. Because I have already told you that only orbital having one electron, when the orbital have only one electron, only then it can overlap with the another orbital of another element having one electron, only then the covalent bond will form. That's why we have excited one electron from 2s to the 2px orbital. So now here we are having two electrons into different orbitals, so beryllium can form now two bonds with two chlorine atoms. Now after that what's gonna happen? Now there will be the intermixing of the orbital having electrons. So here 2s and 2px is having one electron each, so the 2s and 2px will intermix with each other. Here 1s, that's 2s, and 1p, that's 2px, will intermix with each other to form two new hybrid orbitals. I have told you earlier also the number of hybrid orbitals formed will be equal to the number of atomic orbitals mixing with each other. Here 1s and 1p, that means two orbitals are mixing, so here the two new hybrid orbitals will be formed. Now the two new hybrid orbitals will be the degenerate orbitals, that is the two orbitals will have equal energies, and 1s and 1p is mixing, that's why the hybridization will be called as sp hybridization, and we got two hybrid orbitals which are named as sp hybrid orbitals. That means one hybrid orbital is having 50% s character and a 50% p character, and same goes to the second hybrid orbital, the sp. Now what's next? After that, we were having the two electrons, one in 2s and the 2px, so there will be the redistribution of electrons in the two sp orbitals according to the Hund's rule. So the first electron will go in the first sp hybrid orbital and the second electron will go in the second hybrid orbital. Now that's about the beryllium. Now let's talk about the chlorine. We are talking about now chlorine. What's the atomic number of chlorine? That's 17. So the configuration, the valence shell configuration of our chlorine will be, that's 3s2 3p 5. So let's make the orbital diagram in the form of boxes. That's 3s, that's 3px, that's 3py, and that's 3pz. Now here we are having two electrons in s, the 3s, so that's the first electron and the second electron. After that we are having 5 electrons in 3p, so we are going to fill that 5 electrons according to the Hund's rule in the 3p subshell or 3p orbitals. So that's first electron, second electron, third electron, fourth electron, fifth electron. So that's our 3s to 3p5 configuration in the form of orbital diagram of the boxes form. So now what next? Here 3pz is short of 1 electron. Here 3pz is short of 1 electron. If 3pz shares 1 electron with beryllium, then chlorine will attain the stable noble gas configuration of argon. So what's going to happen? What exactly going to happen? That the 3pz of chlorine, so I'm writing over here, just focus it over here, that I'm writing chlorine, the 3pz orbital containing 1 electron of chlorine will overlap with the sp orbital of the beryllium to form the sigma bond, and that sigma bond will be sigma sp and a p. Why so? Because there's the overlapping between the sp hybrid orbital of the beryllium with the p orbital of chlorine. That's why this sigma bond is called as sigma sp and the p. Now let's talk about the another chlorine. We are having two chlorines now actually. So that's a chlorine, and here again the 3pz of the another chlorine will overlap with the sp hybrid orbital of the beryllium to form the sigma bond, and again it is the overlapping between the sp hybrid orbital of the beryllium with the p orbital of the chlorine, that's what sigma spp. Now both the sigma bonds are of same type, that's why the bond between the beryllium and the chlorines will be of equal strength. Now what's the structure of sp hybridization? Here we actually got the sp hybridization, we got the sp hybridization, and case of sp hybridization I have told you in the previous lecture that sp hybridization has the linear structure. So that means we are having the beryllium over here which is forming covalent bond with the chlorine, and the chlorine and the bond angle between them will be of 180 degrees, and that's the sigma bond between sp or hybrid orbital of beryllium and a p orbital of chlorine, and that's also a sigma bond that have been found with by the overlapping of sp hybrid orbital of beryllium with the p orbital of chlorine. So we got the two sigma bonds and its structure is linear. Now let's come back to the hybridization. Here two types of energies are consumed. The first type of energy is during the promotion of electron. I am saying during the promotion of electron or excitation of an electron, the promotional energy is required. And on the another hand, during the mixing of hybrid orbitals, during the mixing of atomic orbitals, or we can say during the hybridization, the energy is required. So I am writing during the intermixing of atomic orbitals, during the intermixing of atomic orbitals, that's called hybridization process. That is hybridization process energy is required, or we can say consumed. Here also required or consumed. But when there's a formation of sigma bonds, the energy is liberated. Here I am writing during the formation of new sigma bonds comma, energy is liberated and promotional energy as well as energy required for hybridization process process is actually recovered or compensated. So the two energies which were absorbed gets compensated during the formation of new sigma bonds. That's why this whole process, that's the formation of beryllium chloride, is possible or feasible. So that's all about the sp hybridization. I hope you got today's topic. So if any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.